programming with JuMP. So basically, it's a JuMP extension so that you can model problems with sets. So instead of just trying to find a variable, you're trying to find a set. So the set programs look like this. So the constraint you can have are like this. So suppose S is a set, T is a set, A and B are matrices. You can, for example, ask A times the set, which means you take every point of the set, multiply them by the matrix, you get a new set of points. Okay, so it's like the image of the point of the set, and this set should be included in this one. For example, a constraint like that. So you can have some sets which are variables you need to find, and some sets that are constant that you already have. You can say a set should be inside some constant set that you already know. You can say some variable set should be inside a variable set. You can also have normal JuMP variables. And so if you say a vector should be inside a set, means what it means. So if the set is an ellipsoid and this is a vector, you can use around the code. If this set is constant and if it's a variable, then you need to use a DP and stuff like that. Either points can either be constant or it can be also variables and so on. So you're basically mixing a program which is using sets and which is using normal variables. And then in the objective, sometimes you want to maximize the volume of the set. So what I try to do here is to extend JuMP to also allow it to create set variable and then reformulate it to something that you can. Okay, so I show a few applications because most of the work I've done in my PhD is always like computing some sets. And so it all like kind of falls down in this framework. So by reformulate everything as using this set prog thing, I can separate the modeling, like what I want to solve, and then the solving, like, oh, I actually want to solve this set program. So first, when you have a hybrid system and you want to show that they're stable, so it's more complicated for a simple system where you just check the eigenvalues. One method is to compute invariant sets. And so you could try to compute an invariant ellipsoid, but sometimes it's not enough to show that it's stable, and so you need to increase the degree, and then you can have some more sophisticated sets. So this is degree 2, ellipsoid, degree 4, 6, 8, and so on. And then if the SDP program tells you I cannot solve the problem, it's infeasible, I cannot find a problem of a set of this form which shows stability of the system, then if using the infeasibility certificate of the PhD program, if it's low rank, in fact, I may be able to prove that in fact the problem is unstable. So there is no variant set even if you don't specify any shape. That's the reason why ProxSDP may help if it can give me a low rank. Then in information theory, there is this entropic cone set, which you can also, we don't really know which representation, but we kind of know an implicit representation as a solution of a set program. And there is some question like, what is the maximum value, the maximum you can go in some direction. So this is if you take 4 like random variables, it's a set in 15 dimensions, but if you cut and project it in some way, you get this. This is like another approximation that was given by Shannon initially when he defined the entropy, but like it's another approximation. There are points inside here which are invalid, and we'd like to remove it using this set program. And basically, what you can do is if you try to see what's the maximum direction in the maximum the point the most in this direction, which is also entropic, it's somewhere here, and so you need to add some cuts to have the exact one. So there is one cut that was found like in 2000, and then also to show that in fact all the Shannon inequality were not enough. And then if you run some kind of SDDP, you can find other cuts. So one way to solve this set program when the set you would like to find is a polyhedron, and you don't want to maximize the volume, but just in one direction, you actually use SDDP. So that's something I presented there. So I won't go into the detail. I prefer to focus on like how I did extend JuMP to have this API. So you can also compute control invariant set. It can be useful in MPC. So here you'd like to find the maximum invariant set in this rectangle. So if you try to use polyhedron, it won't work because the maximal invariant set is not a polyhedron, so you need to, at least it will never converge on the exact one. If you use some approximation, it may work. So here I tried with ellipsoid, you get this, and then if you use higher degree, you get a larger one. So it's in 4 dimensions, so I have just shown my projections. And then I also presented one application to stochastic programming where you want to, by the safety here, you don't want to have no water or too much water. Again, this invariant set problem here. The optimal solution is actually a simple polytope shown in yellow, and if you try to find an ellipsoid instead, you get this blue one. Okay, so basically the main idea is you always kind of a set program, and then you can either say, I want to find a set which is a polyhedron, and then use some method, or I want this set to be an ellipsoid, and use different method, and you can say, I want the set which is a sublevel set of a polynomial, and then you can have more sophisticated shapes like that. And what I'd like to do is to separate like the modeling, like what do you want, and then what kind of set do you want to try with, and then what is the method you want to do. So that you know that if the model is the same, you just change the method, it's just a different method. The same thing that we have in optimization is kind of nice to be able to write this optimization problem and say, okay, just change the solver. Just a different method but solving the same thing. So it kind of clarifies. So here is how it looks like. Suppose you want to find a set which is an ellipsoid. It should be inside some square, so I've defined it before with polyhedra. I use the Unicode to represent the fact that it's a square, but that's just a variable name. And then I have some matrix E and A and E that do not show, it's not important. I want this, also this constraint to be satisfied, and then I want to maximize the volume. And in fact, the end fruit of the volumes, because this can be reformulated into second order code and PSD. I have some solver, it doesn't matter, and then I optimize, and then once it's optimized, I can ask the value of this variable and actually give me an ellipsoid I can plot. So it's the idea. So I use the variable in the constraint macro, just like with regular variables, except that here it's sets. So I need to extend them in some way. I will explain to be able to create ellipsoidal variables and also to have this weird sense, which is not recognized by JuMP. So if I want, instead of maximizing like the volume of the ellipsoid, instead you want to maximize the sum of the square of the axis. It actually corresponds to the trace of the ellipsoid. So it's you can use this. And it actually corresponds to the integral of the ellipsoid in the square from -1, -1 to 1, 1. And the advantage of this is that it's easy to generalize to polynomial, just integrate polynomial, and the volume of a polynomial sublevel set is hard to find. Okay, so if I solve this problem with polyhedron, I get this yellow one. It's a simple solution. If I solve it with ellipsoid, depending on whether I use the trace of the volume I use, I get a different one. So it's not just the maximum volume ellipsoid, it's the maximum volume ellipsoid satisfying some constraint inside the square. So this is the square variable. This is a constant, the green square, and then if you solve the problem, and here you say polyhedron, you would get the yellow one. If you say I want S to demand to maximize the determinant of S. So if you solve this program, you will get the blue one. And then if you replace this line by this line, you get the red one. And then suppose you don't like this, you'd like to be closer to the yellow one with, but using SDP, then you could, so one important point that it also does is that, in fact, when you want to compute ellipsoid, you always have two choices. You can either represent your ellipsoid like you can say it's the set of points such that x transpose qx is smaller than 1, or x transpose q minus 1x is smaller than 1. So what I say is that this is the actual representation of an ellipsoid. And this is actually, if this is the representation of your ellipsoid, then the polar of your ellipsoid would be x transpose qx more than 1. So in fact, I like to say that this matrix is actually the matrix that represents the polar of the ellipsoid. And so with that, you need to choose, do I want to parameterize the ellipsoid of its polar? And this actually depends on the problem. So in this case, because of this constraint, you would like to have the polar representation. So instead of trying to find the ellipsoid, you're trying to find the polar. And once you found the polar, you take the polar and split in the matrix, basically. Because when you have found the matrix, it's easy to take the polar, but once you're trying to find, it's a variable, so you cannot.
And is that choice automatic?
Yeah, it's automatic. It's
when it sees those.
Yeah, it's automatic. And if both work, it uses the primal. So in this case, in fact, it solves this problem, the polar problem. So the polar of the square, it's this one. The polar of this yellow set, it's this one. And then the polar of the blue one, it's this one. The polar of the trace is this one. In fact, when you take the polar here, the inclusion, it's the opposite. So instead of saying that you should be inside the square, the polar should be outside. Okay, so if instead of finding ellipsoid, I want sublevel set of polynomial of degree d. So polynomial, they could be non-convex. I want them to be convex, because otherwise the polar doesn't make sense. If you want to find a non-convex set, you would say it doesn't work. If you want to find a convex set, you can take the polar and do the polar trick, it works. You'd like it to be symmetric around the origin and of degree d. And for the volume, you use the integral of the polynomial of the square. So if you do this, you see that by increasing the degree, you get closer and closer. So with the red one, I think it's degree 3, 4, 6, 8, 10. I think it's 10. No, it's not. And I think, no, I've not shown, it's like 24, something like that. Degree 24. You're actually very close to the yellow one. And in fact, what it actually did is solve it in the polar. So this is actually the sublevel set of the polynomials we have computed. So then the best one is this this red one.
Sorry, how are you getting the volume of the sublevel on the?
So I integrate the polynomial in the square. So basically, and because it's homogeneous, it's actually a good way. So it's an idea that was given in a paper of Didier. They're also trying to find a polynomial, and they say that this is a kind of a good heuristic. Okay, so that's basically what it does. Now, what I like to do with the second part is actually show how you can extend JuMP to be able to have this nice syntax, which is very familiar to the user, which is accustomed to JuMP. So first, how do you create these custom variables? So basically, it's the same way we do it in PolyJuMP and sum of squares. You just add, so here is the name of the variable. You can use containers if you want. But here you add a new, another parameter, which is like the type of the variable. And also passes the keyword in variable type. And what happens if you pass this is that in JuMP you will get an error because it will call build variable. So it will give this custom error function. If you call it, it gives a nice error function where it also shows what is the macro that was called. It gets the variable info just like if it wanted to create a scalar variable, but it also gets this, which is exactly the third argument. And so just by adding this new method, you're actually going to get the code, which is called inside the macro. So that's a way to extend the macro without the need to create a new macro. So in this case, if the user gave the lower bound or upper bound to the variable, it actually doesn't make sense for our set. So it just throw an error. But with this nice, with this function, it will be a nice error which will say that the error happened putting this macro. It will show the code of the macro and so on. And otherwise, we just return the set. And then JuMP will code add variable with this set and with the name. And what we do at this point is that we don't, so we know that we need to create an ellipsoid, but we don't know what's the dimension of the ellipsoid. So we have not said that. We've not said that the ellipsoid was 2-dimensional. It actually guessed that because the square is 2-dimensional. And we also don't know if we're going to represent this in the primal or the polar way. So we cannot really create anything at this point. So we just remember that, okay, this is a ellipsoid. So we have a set variable reference, which is like variable reference, but for sets. And we return that. And then we keep internally a list. So the JuMP model has a dictionary of extension that you can, when you can stuff information that you're an extension and that you need later. And so when the user will call optimize, only then we will actually create everything, because then we will have the full information. So that's a difference between like the polygon sum of square extension, where you always have all the information. When you create a sum of square constraint, you directly give it to the solver, and there is nothing that is kept, and there is no solve hook. Here, there is an optimized hook, as we will see. So second, how do you do this? So I had to take a screenshot because LaTeX doesn't recognize this symbol. So how do you do it for the custom sign, so the inclusion sign? So we want to be able to use the inclusion sign, the constraint. So JuMP, what it does, so we've talked about the build variable, add variable, build constraint, add constraint yesterday, but there is also the parse variable and the parse constraint. And these are called, you don't see them when you say macro expand, because they are called at the compile time, if you want. Actually parsing them at the parse time. And so it's trying to parse that something is, and so what is nice is that the sense is given in a val. You don't really see here. It's a val which is defined in base. So in fact, you can add a new method, because val has a different type for every sense, for every symbol. And so you can actually create a new method that will be called. So when there is this sense, you will get the call, and you know that you have, the user has asked this to be included in the right-hand side. And so we'd like to come back to a normal JuMP constraint. In a JuMP constraint, normally you say something is inside a set, and not a set is included in a set. So what we do is I define in the power set, the set of all the subsets. So what I can say is that this set is included in the set of all the subsets, the same array. So no, this is a classical JuMP constraint with something inside. So then here you need to create the code that JuMP will execute. So depending on whether it's vectorized or not, you have to add a dot. You can check in JuMP for the example what it does, and it's basically the same. And so what it needs to create the constraint is called base constraint with this left-hand side inside. And then also, if you use the reverse operator, it just falls back to this one. And if you use the strict one, I just say this is not clear. We don't do strict inequality. Strict exclusion, only non-strict with an equal. Okay, so that's how you parse it. Now, when the user, you will, in the macro, you will go to build constraint. You will receive this set inside a power set. So again, this JuMP will not recognize this because it doesn't know this type. And so what you do is you create a constraint object, right? So just like I explained in the tutorial yesterday. So you create an inclusion constraint with some set and then the other set. And then what this is, when you call add constraint, again, JuMP will not recognize this. You only know scalar and vectors constraints. And what you'd like to do is, it actually depends. So in fact, this has like fallbacks, because if the subset, if like the subset of the power sets, if you already here, it's because ellipsoid that you don't know how to represent them yet. But for some other things, you know. For example, if you want to say a vector of variables is inside an ellipsoid, which is a constant, that you can immediately know what to do, because the ellipsoid is a constant and the vector of variables are already variables. And so that you don't store them for later, you can immediately rewrite it and give it to JuMP. But for this one, because we don't know yet how to represent the set, we just store it in some vectors, and then at the end we have an optimized hook. So when you call optimize to JuMP, we have set a hook, and so it will call us. And so what we do, we clear space if there is already an optimizer which was called, and then we check, okay, what's the dimension of the ellipsoid? Should be polar, primal, and we actually create things. And then we load, which is, so for all the constraints, now we transform them to OTP and so on. And then we call the JuMP optimize. So what it does is, again, it's going to go through build constraints. So, and now the ellipsoid will actually be, it will actually be real ellipsoid with the matrix and so on. So this is what would have been called if you had a real ellipsoid and not a variable ellipsoid for which you don't really exist the representation. So it's actually, which is nice, and you can reuse the same code. And what you do is, well, the inclusion ellipsoid, once you have the PSD matrix, it just, this should be PSD. You can just redirect to the build constraint that JuMP knows, a symmetric matrix in PSD code that JuMP will know, and it will do the rest of the work. So you can actually do all the transformation in build constraint, which is nice. So yesterday I showed how to do transformation in the bridges. That's useful when the set, you can actually, some solver may actually support the set. You can also do just a transformation in build constraint. Then the solver will never see that, in fact, there was this set. And then if you print the JuMP model, you will just see this, because JuMP will also not see that, in fact, the constraint was like that before. That's a bit the pros and cons. Then if you say a polar should be included in another polar, then what you do is that you do the polar of the two sets and you reverse the inclusion as we've seen that's equivalent. Then if you say, for example, a polar representation of a set should be included in a half space. So it's the same as if you say this point. So the half space is AX smaller than B. If you take this point, so A, you know that A over B X should be smaller than 1. And so in fact, this means that this should be inside the polar. So you take the polar representation, you say this point should be inside the polar, and this is implemented. So in fact, you can reuse a lot of things by playing with these things. So what I want basically to show here is that you can, with build constraint, you can play with like redirecting to other build constraint codes, and that's basically how I've implemented everything. Yes. But in fact, I'm done. So conclusion. So currently, the representation of the set. I have some custom submodule in the package, but we've just created a mathematical set with Marcello here. And what's nice there is that we will define many sets, but like in a completely generic way, and that could be reused by any application that needs this set. For example, an ellipsoid represented like that. It has nothing even specific to optimization. Some people may just want to build it and plot it, and that's it. So in this package, we could just define ellipsoid, define a receive to plot them, and common utilities, and I don't have to re-implement, for example, this in my package. And same thing with sublevel set of polynomials and other stuff like that, or square, all the square, the rectangles, and all these shapes. So in fact, the only thing as implemented is like the ellipsoid and the polynomial sublevel set, and not yet the computation as using polyhedra solver. So when I showed the yellow solution, like here, it was computed manually, not through set probe. But it's a future work. And it could use a polyhedra library like CDD and so on, but also lazy set, which could use different templates and would actually work in more cases. And then, so the example I showed initially in information theory, when you actually want to optimize in some direction, there are other applications, even in control, when you also want to do that. So it's easy to formulate that with ellipsoid and polynomial. I think this already works. But then if you do that with polyhedra, it should use SDDP automatically.